Okay, so today's focus is going to be on the lab. But if you have any questions, we'll address those first. So, does anyone have any questions? You can also ask questions about the measurements lab. Go ahead, Anurag.
Hello.
Hello.
All right, but I already submitted to the measurements lab. I have one question about the results.
Yes.
So on the document, it says you only want the results for the card area,
Yes.
and that's it, right? Or do
That's
you want?
pretty, that's pretty much the results.
All right, okay. I thought you wanted more than that, but that's fine.
The rest of that is data, like the length, the width, um, the mass of the paper card or paper ruler, the mass of the store ruler. The rest of that is data.
All right, so did you want it in a table or did you want it written out for results?
There aren't many results there. You can put it in a table or not.
All right, okay. Thank you.
Usually tables are for things like where you have more than 3 things or something.
All right.
Okay, good. Anyone else with questions? Okay, that being said, let's take a look at today's lab. I'm going to change my share screen to my browser, which is Firefox. And you can see that we have the density lab here. And let's see, which section am I in? I'm in 53. So I'm going to go to the measurements lab, or excuse me, the density lab. And hopefully you can see what is on my screen. If you can, give me a thumbs up or a yes or something like that. If I see enough, I'm going to go ahead and keep going. Okay. So you'll notice that in your lab notebook, you're supposed to write this up with a title, intro, safety, procedure, data, calculations, results, and discussion. You're supposed to submit a photo of your graduated cylinder with the pennies in the water. And it's really a close-up of the meniscus. And here, this is just so that I can see that you're reading the volume correctly. That means I'm going to need to be able to see the numbers on the side of your cylinder also. And you have to be careful to make sure that the camera is at the proper height. And we talked about that with the ring that goes around the cylinder at every 10. And you want to answer the questions at the end of the lab and submit answers. And then here I give you a little bit of the background. I'm not going to go into detail here. The assumption is that you've read this before coming to class. Learning objectives, materials. There is no safety here, but we'll talk about that in just a moment. And then here's the procedure. And you can see that I have the data and the calculations. I tell you what to do for the results table and for the discussion. And now let's go back to the very first part of what you need to submit, and let's talk about these items in a little bit more detail. So for the title, in my opinion, you should just call it density. For the introduction, you should talk about what density is. So density is mass divided by volume. You should tell us what you're going to be doing, and what you're going to be doing is you're going to be determining the density of pennies and dimes, and you should tell us how you're going to do that. And the answer is you're going to mass the pennies with a scale, and you're going to determine their volume by water displacement and by geometric shape. So you're actually going to get 2 densities for the pennies, one where you use the volume by water displacement, and the other where you use the volume by geometric shape. And then you're going to do the same thing for the dimes. You should also write up in your introduction something along the lines of, well, you know that pennies and dimes are made out of copper and zinc, and because pennies look like they're made out of copper, you think pennies are made out of copper, and dimes look like they're silver, so they're probably made out of zinc. And that you're going to test this assumption by comparing the densities you get with the actual densities of copper and zinc to see if they match. So you want to put all of that in your introduction. For the safety, even though I haven't written anything in this document about safety, you should address safety. If you read through the procedure, you'll see that there's nothing in there that would make you be wary about using anything. Water, dimes, it's not a big deal. So you want to write safety. There are no safety issues for this experiment. For the procedure, what I have written below is pretty much what you want to write into your book. I mean, there's not much you're going to do to deviate from the procedure. And the same with the data. Now, remember, part of this lab is practicing measurements. You're going to be making measurements and you want to be recording the correct measurements. So when you're measuring the penny and you're measuring its geometric shape, make sure that you measure correctly and record correctly. They're the same thing, the measurement and the recording. There should be the same number. And it's the same when you're using the graduated cylinder. Measure and record correctly. Okay, so here I give you a little bit of background. And again, I'm not going to go into this, although I think there's a couple interesting stories in here. The one about Archimedes and the other one about 2 bits. So you may have heard of the term 2 bits, that'll cost you 2 bits. That means a quarter. And this gives you the reason why 2 bits is a quarter. Okay, so I normally in my lab don't write learning objectives and materials, but the procedure again is right here. The data, pretty straightforward, I think. The calculations based on the assignment. So now let's jump to the assignment. So here's the assignment. If you read question number 1 and question number 2, 3, 4, and 5, and 6, there are no calculations there. So none of that is going to end up in the calculation section. That will be answered in the assignment. And I would, if it were me, I would put the assignment after the discussion. Now, you do want to read the assignment before you do the lab because this will give you some things to think about during the lab. So if we look at question number 1, a student puts the pennies in a Ziploc baggie so they do not get wet during water displacement. This is a true story. How does this affect the water displacement volume of the pennies? i.e., is the determined volume too large or too small? You know, for me, I would say, well, you know, the baggie itself must have some volume. So I'm getting the volume of the pennies and the baggie. And therefore, the volume I'm getting is too large if I think it's just the pennies. And then for number 2, you could say, well, if the volume is too large, and that is in the bottom of the density formula, then that means my density is going to be too small. Okay, so these are the types of things I'm expecting for explanations. And 3 is, why are 50 pennies used for determining density by water displacement? And why is only 1 penny used for determining density by geometric shape? So clearly with 3 and 4, I don't need to write explain because the question itself is asking for an explanation. And then I expect you to tell me which method you think is more accurate and give me an explanation. Then you look up the densities of copper and zinc using webelements.com. And I'm going to do a little editing here. So I'm going to go to edit. I'm hungry. Did anyone bring me something to eat? Like an apple or something? Maybe a virtual apple? No one? Has anyone tried the Cosmic Crisp apples? I really like those. They're really good. Okay, so what I'm changing here is, do you see how number 6 says, look up the densities on webelements.com and report the values? And then it says, convert the densities found on Web Elements. I'm going to put .com just to be consistent. Okay, so let me save this. And what we're going to do is now we're going to go to webelements.com. Webelements.com is a great website that chemists like because it gives you a lot of facts about the different elements. Okay, so here you can see a periodic table of the elements, and I'm going to go to copper, and I'm going to link to copper. And you'll see that they give you all sorts of information about copper. And in some cases, they actually have a audio that describes the particular element. So here we see this copper description, and I press that little speaker.
Element 29, copper, is one of the most important metals. Copper is reddish with a bright metallic luster. It is malleable and ductile. It is a good conductor of heat and second only to silver in electrical conductivity. Its alloys, brass and bronze, are very important. Monal and gunmetals also contain copper. Apparently, the reason that policemen in the USA are nicknamed cops or coppers is to do with their uniforms, which used to have copper buttons. The most important compounds are the oxide and the sulfate, sometimes known as blue vitriol. Copper reagents such as Failing solution are used in analytical chemistry in tests for sugar.
Okay, so nice little background of copper, not comprehensive, but just interesting. Now, if I scroll down, you should be able to see here that this does give us some physical properties, and one of those physical properties is the density of copper. And I'm going to write this number down, 8920 kilograms meters to the -3. And what I'm going to do now is I'm going to switch my share because, well, I'm not going to switch my share yet. I'm going to go back to the lab. And can you see how questions, I believe 6 or 7, I can't remember which. Oh, I got to get rid of that rubric. So if we look at number 6, we look these up and we find the values. Before I move on from that, I do want to go back to this. If you want to find the values for zinc, over here on the left, you can go back to the periodic table, or they give you a little window of other elements that are near copper that you can pick. And so we can switch over to zinc very easily. Okay, so number 6 says look up the values and report them. So now I'm going to change my share. And number 7 says convert from kilograms meters to the -3 to grams centimeters to the -3, i.e., that is, from kilograms per cubic meter to grams per cubic centimeter. Okay, so let me do my switch share. And you should now see the desktop. Okay, so what we're going to do here it's always hard to adjust this so that the camera's out of my line of sight and the paper is in the middle of where the camera is. So this is the value for copper, and we need to turn this into grams per centimeter to the -3. The above is the same as kilograms meters cubed, and we want grams per centimeters cubed. This is a common way of writing things in the numerator when you're a physicist. You just take whatever's in the numerator and change the sign. So these mean the same thing, and I'm going to prove it to you. So here's what's reported by Web Elements, and I'm going to multiply this by meters cubed over meters cubed. So I'm multiplying by 1, which means I'm not changing this value whatsoever. It's the same amount. So a meter to the -3 times a meter to the +3 is a meter to the 0 power. A meter to the 0 power is 1. So the top becomes 8920 kilograms because this meter cubed and this meter to the -3 cancel. The meter cubed on the bottom does not cancel. So I've changed this to kilograms per meter cubed instead of kilograms meters to the -3. So these mean the same thing. I prefer this bottom way rather than this top way because I'm not a physicist. Okay. So our job is now going to be to convert this 8,920 kilograms per meter cubed to grams per centimeter cubed. So I think you know how to convert kilograms to grams, and I don't think you know how to convert centimeters cubed to meters cubed, but you do know how to convert centimeters to meters. So this is one of those things where you use centimeters and meters, that conversion, and you use it 3 times. So I'm not going to show you how to do that because there are plenty of examples in the module videos, and we've done this one with different problems with area and with volume. Okay, so now I'm going to go back to the questions. And so I'm doing a new share, going back to the website. So here we go. So number 7, convert the densities. And here, since that's a calculation, that's probably something that you want to show in your calculations above. And the reason you want to show that in your calculations above is because you want to make the comparison of the densities you find to these densities. And the densities you're finding are going to be in grams per centimeter cubed. Number 8, you're going to say, well, I think pennies are both mostly made out of this based on the density, and so forth and so on. Number 9, look up the density of a penny minted after 1983, calculate your percent error. So I'm going to show you how to calculate percent error. So I'm going to do a switch screen. And now you should be able to see my arm. And I'm going to make a little line here. And I'm going to show you how to calculate percent error. So with the percent error, you're going to start off with the density that you determined. So your experimental value. You're going to subtract from that the accepted value, and we're going to go ahead and use the accepted value of copper that you find on the internet, or zinc, whatever the metal happens to be. You divide by the accepted value, and you write times 100%. So that's how you calculate your percent error. You're going to do that for the pennies and for the zinc. Any questions about calculating percent error? So what does EXP mean? Your experimental value, the one you determine. This is the one you look up in the literature, and sometimes it's written this way: experimental minus literature over literature times 100%. It's also written this way: accepted. Literature just means the internet. Now, when you look up the values, you want to go to a reputable site. So Web Elements is a reputable site, whereas .Tony is not a reputable site. Okay, not well respected. Heck, it doesn't even exist. Okay, so make sure you go to a well respected site. So usually a .gov or .edu. Those are usually pretty good. But I'm telling you, webelements.com is really good. Okay, any questions about calculating percent error? If you have one, go ahead and raise your hand. If not, we're going to move on. Okay, I'm going to go back to the lab now. And here you can say, look up the density of a penny minted after, oh, I'm sorry, I made a mistake. For your accepted value, use the density of the penny that you find online. You should be able to find that. And 10, you're going to use the density of the pennies to determine the cubic centimeter volume of 30 pounds of pennies. Now I'm going to back this up a little bit, and we're going to look at calculations here because some of them can be tough. Some are very easy. So let's look at an easy one. Calculate the mass of water and the density of water. So for the mass of water, and I'm going to change my share with you in just a moment, you're probably going to do something like this in your lab notebook. So I'm going to switch my share once again. So we're calculating the mass of water. So I have the mass of water is going to be the volume final, or excuse me, not the volume final, the mass, and actually I don't like to use an uppercase M. Mass of the water is equal to the mass final minus the mass initial. So the mass final is the graduated cylinder with the water, and the mass initial is your graduated cylinder without the water. So that's going to be the mass of your water, the density of the water, and here you're going to put in actual numbers here. And if this is your graduated cylinder, so this is your graduated cylinder. What precision should we be able to measure to? Should we be able to measure to the tens? Absolutely. How about to the ones? Absolutely. How about to the 10th? What do you think? 10th of a milliliter. That's a yes or no question. So let's take a look here at a drawing of what we see here. And I'm going to flip this around just a little bit so that it looks like 60 and 70 there. The way you figure this out, and this is something we should learn in the measurements lab, is the following. If this is 70 and this is 60, and there are lines that look like this, that means that this line right above 60 is 61. And therefore, the two closest lines are 1 milliliter apart, so that we should be able to measure to 0.1 milliliter. It might be 0.0, it might be 0.1, it might be 0.2, 0.3, 0.4. So I'm expecting what you've learned in the measurements lab, you're going to use in this lab. So you're going to put these, what I ask you to do here? You're going to measure to the 100th of a milliliter. The density is going to be the mass of the water divided by the volume of the water. So you're going to put your mass here, your volume here. This will be in grams. This will be in milliliters, and your answer will be in grams per milliliter. And you want to report the answer with the correct number of significant figures. So you should show both of these calculations in your lab write-up. So now I'm going to go back to the lab itself. So this is what I mean by showing the calculations. There's another calculation I want to show you. If you look at the volume of 1 penny by geometric dimension, let me show you how to do that. So I'm going to change my share. And we're going to look at my tabletop again. And we're looking at the volume of the penny by geometric shape. So the penny looks like this from the side, and it looks like this from the top. So this is the area of the penny on the top, and this is the corresponding area in my other drawing. Here, this distance here is the height of the penny. Now, normally when you have a cylinder where the height is less than the diameter, you don't call it a cylinder, you call it a disc, and you talk about how thick the disc is. Like a pancake is a disc, although it really is a cylinder. And you don't talk about how tall a pancake is, you talk about how thick it is. But we're going to use H for the thickness. So if you want the volume of a penny, you're going to do the area times the height. The area of a circle is pi r squared. So this is how you would calculate the volume, the geometric volume of the penny. Now, it's nearly impossible to measure the radius, but you can measure the diameter. And we know that the radius is half of the diameter. So when you're doing this calculation, you probably want to do this first. Calculate the radius by putting the diameter in there, and remember to pay attention to significant figures. And then once you have that value, you can use this formula. And let's see, I have a penny here. So here's a penny, and you're just going to use your ruler to measure the diameter and how tall it is. And remember, you're measuring in centimeters, and you want to measure as best as you can. Okay, now there's another formula you can use here so that you don't have to use this formula. And it basically looks like this. You'll notice I put parentheses around the R because that's okay. Since R is the diameter divided by 2, I can put diameter divided by 2 in parentheses. And then I can get rid of the parentheses by squaring the diameter and squaring the 2. So you can use either of these methods for calculating the volume by geometric dimension. And when you do it this way, you have to do 2 calculations. And when you do it this way, it's just 1. That's why I like the bottom way better. So are there any questions about calculating the volume of a penny by geometric shape? Okay, you would do the same thing when you're calculating the volume of the dime by geometric shape. Okay, so when you get the density of the penny, you're going to get the density of the penny using displacement volume, and you're going to get the density of the penny using the geometric shape. And when you do it by density, or by, displacement, you're going to have the mass divided by the volume by displacement. And when you do it by geometric shape, you're going to do the mass divided by the volume by geometric shape. So hopefully these two values are close to one another when you're done with the experiment, but they probably will not be identical because probably one of these methods is better than the other. And that's one of the questions in the assignment. If we take a look, and now I'm going to go back to the assignment. If you take a look at the assignment, which method for volume determination, water displacement or geometric shape, should be more accurate? Explain. So you'll find out which is more accurate when you're done with the lab. Are there any questions so far about the lab and what you should be doing? Okay, so we've talked about all of the assignment here. We've talked about the calculations, and now it's time to look at the results and the discussion. So the results are straightforward. Make a nice, neat ordered table for each density. And for the discussion, basically tell you that it should start with the density of the pennies was determined to be, and the density of the dimes was determined to be. Comparing these with the densities of copper and zinc, we find that, yeah, pennies are made out of copper. And yeah, dimes are made out of zinc, and the hypothesis was correct. Or you might say, wow, pennies are not made out of copper, they're made out of zinc. That sounds crazy. And dimes are made out of copper. And the original hypothesis was incorrect. So this is part of doing science, is sometimes your hypothesis is correct and sometimes it's incorrect, but you address it no matter what. Another thing you want to address in your discussion, which I haven't written here, is you want to look at things like your percent error. So based on your percent error, why do you think you were a little bit off? Okay, you want to give an explanation. So that's the lab you should be working on today, tomorrow, the next day. You don't want to wait until the day it's due to start the lab. That's always a bad idea, because number one, when a lab is due, you may or may not be able to contact me quickly. And if you're contacting me at 10 o'clock at night, the day the lab is due, you're just going to hear crickets because I'm not going to respond. So you want to start these labs well before they're due. I would say at least the day that they're that we talk about them in Zoom sessions. So you should start this today so that if you run into any problems, you can write questions about them quickly. So any more questions or any questions about the lab? That's a yes or no. Any questions about the lab? Okay, 2 out of 4 is good enough for me. I'm going to move on. So we have until about 2:30 to go over more material. So I'm going to use the rest of this time to cover problems from the back of the book. And if you want to duck out, you can. I don't mind. This is going to be recorded and posted. But I'm going to go over more problems from the back of the book in preparation for the eventual exam and quiz. Okay, so let me change my share. And we're back to the tabletop. And you can see that we have already covered this problem here, number 2. And I believe we are now on number 18. So let me show you how to approach this problem. And I need some blank paper. Here we go. So this is on page 50. This is more of the converting. A 2-inch piece of chocolate cake with frosting provides 1,670 kilojoules of energy. What is this in dietary calories? And this is an uppercase C. So we want to take our 1,670 kilojoules and convert that into calories. So if we map out a way to do this, we can take the 1,670 kilojoules, turn that into joules. We can take the joules and turn that into lowercase calories, and then turn that into kilocalories. And the reason we want kilocalories is because calories and kilocalories mean the same thing. So this is the way we could do it. We just need the relationship between these 3 arrows. So kilojoules and joules, we could write 1 kilojoule is equal to 1,000 joules. Now, would you bet your bippy on this conversion? That is, would you bet everything you own that this is correct? That's a yes or no question. Okay, 3 of you would bet everything you own on it. Can you prove that it is correct? That's another question. Can you prove that it is correct? Okay, Sadie says she can. On your job, you think you can, and destiny. So let me show you how you can prove that it's correct. I'm just going to get rid of all the prefixes. K means 10 to the third. Now I'm going to take that and expand it so it's not 10 to the third. So check, it's correct. So there's always a way to check your conversions. So what I want you to do is check this conversion and see if it's correct. Check that one and see if it's correct. And when you're done, just give me a signal that you're done. The signal can be yes, it can be no, it can be thumbs up, it can be clapping hands. Just give me a signal that you're done. So I'm going to put a little question mark. It is really windy where I am. Probably windy where you are too. Hope those redwoods don't get knocked down. Okay, I am not seeing a lot of response here. So I'm going to go ahead and show you how to do this. So to check these, you take the prefix and put the number there that really it represents. So milli really represents 10 to the minus 3. This milli is really an imposter for the real thing, which is 10 to the minus 3. What does nano mean? 10 to the minus 9. So I have gotten rid of the prefixes and put numbers there that represent what the prefix is intending to mean. When I have 10 to the 6 times 10 to the minus 3, we add the powers together. So 6 and negative 3 adds up to 3. So if we take a look at what we're left with down the bottom, it says 1,000 meters is 1/1000th of a meter. And is that correct? No way. So that means this is not correct. So let's try it the other way around. Let's try 1 millimeter is equal to 10 to the 6 nanometers. And let's check that one and see if it's correct. When you're done, give me a thumbs up or a no or a yes. So when you're done with this problem, I'm looking for 2 or more responses before I move on. There's 1. Remember, and there's 2. Your response doesn't make the claim that you're saying you're right. You're just done. Okay, so we have 1 times 10 to the minus 3 meters, because milli means 10 to the minus 3. Nano is 10 to the minus 9. So here we've done the substitution. When we simplify this, we get 1 times 10 to the minus 3 on this side, and 6 and negative 9 is negative 3. So check, it's correct. So there's a way to check your metric conversions. So let's get back to the task at hand, which is converting 1,670 kilojoules to calories. And that's uppercase calories, which is the same as a lowercase calorie, but 1,000 of them. Oh, you can't see any of that. My apologies. There you go. Must be a great day at the beach, but you got to stay away from the breakers. So I had written before that I'm going to take the kilojoules, turn that into joules, turn that into lowercase calories, and turn that into kcals. And I had 1, 2, 3. So for number 1, we have 1,000 joules is 1 kJ, kilojoule. For number 2, we have 1 calorie is 4.184 joules. This is something you need to memorize. It's not exact, whereas the one above is exact. Someone earlier today asked, well, why is this one not exact? And the answer is that the joule measurement was made or determined without using water, and the calorie size is based on water. And 3, we have calories and kcals. So 1,000 calories is 1 kcal, like above. 1,000 is 1. And I'm going to cross that off so it looks more like a lowercase c, so that we're good. Okay, so let's see how we put this all together. My lights are flickering, so we may be cut off. So we're going to do 1, 2, 3. So we're going to use these dimensions to decide what goes on top and what goes on the bottom. Some people like to put a 1 underneath here so that it helps you to recognize that this number is in the numerator. And of course, you can't put the 1 on top because this does not mean the same thing. So that would be incorrect. So if I look at number 1, I want to put one of these sides on the bottom and the other on the top. And since I want to get rid of kilojoules, I'm going to put the 1 kilojoule on the bottom so that kilojoules cancel. And I'm going to put 1,000 joules on top like that. Now I'm multiplying this value by 1 because this top value is equal to the bottom value. And therefore that ratio is 1. For number 2, I'm clearly going to put 4.184 joules on the bottom and 1 calorie on top. And the joules cancel. And for this last one, if I want to cancel calories, I'm going to put 1,000 calories on the bottom and 1 kcal on top. And with something like this, we can estimate our answer. 1,000 divided by 1,000 is 1. So I just need to worry about 1,670 divided by 4. And that may seem like a tough thing to do, but just pretend that that's 1,600 divided by 4, which would be about what? 400. And we can reverse engineer this. Would 400 times 4 give us around 1,600? And the answer is yes. So we know our answer here should be around 400. And this has 3 significant figures. This is infinite. This is infinite and 4, and this is infinite. So when we're looking at 3 infinite, 4 infinite, the number of significant figures we're going to have are 3 in our answer. So 1,670 divided by 4.184, and I get 399 kcals. So we have successfully converted. And on an exam, what I'm putting in the block is what I would expect to see for your answer. You don't need to show me all of this work here. You don't need to show me the map. But you may want to do those things because it helps you figure it out. Now, because this is Chem 1A, go ahead, Destiny.
On an exam, do you want us to circle the answer as well?
Not normally, no. If your exam is written well, I will recognize it as the answer. And part of your grade is based on organization. So if you have stuff scattered and I can't tell what's what, you're not going to get full credit. Does that answer the question?
Yeah, thank you.
Okay, so if you want to block it off, that's fine too. Now, since this is Chem 1A, I'm going to show you another way to do this problem. And it's based on this idea. So this is a conversion that you can learn, 4 significant figures exact. I'm going to multiply the left by a K and make this 1 kcal. If I multiply the left by a K, what do I have to do to the right? And the answer is multiply it by K. So I'm going to make this a Kj. This is an equality that is good. So I can take my 1670 kilojoules and convert it directly into kcals using what I have above. So I'm going to put a little 1 here and a little 1 here. And then I'm going to write out the solution over here on the right. Actually, I'm not going to write out the solution on the right. You're going to write out the solution and the answer. And when you're done, give me a little thumbs up or a yes or whatever, and make sure you're using this conversion. I'm looking for 2 or more responses before I move on. Well, that is some fierce wind. And remember, when we move on, I'm just looking for 2 or more responses. It says you're done. You're not claiming victory. You're just claiming that you're done. Okay. So here, if I'm going to use this, I'm going to put something in the denominator to cancel the kcals. So I'm going to put 1 kcal in the denominator so that these cancel. So if I put that in the bottom, the other part has to go in the top. Uh-oh. Do you see the mistake I made between here and here? Who saw it? We're converting kilojoules to kcals. I wrote 1670 kcals. So what lesson have we learned here? Well, 1, Tony's not perfect. And 2, we need to pay attention to what we're writing and make sure we're writing it down correctly. So we're starting over, 1,670 kilojoules times, and there's our conversion. So give me a little thumbs up or a check if you're done. Okay, we've got a couple of responses, so I'm going to go ahead and move forward. So I'm going to put 4.184 kilojoules on the bottom. And I'm going to write 1 kcal on top. And here, I even like this better than above because here I've got 4 zig figs, here I've got 3 zig figs, and the 1 is always exact in these conversions. So I have less numbers to look at for calculating zig figs. So I want 3, and I get 399 kcals. So if you had written this down on your test instead of this, it would be perfectly acceptable. Any questions about that? Yes or no? Okay, that's a question, Sadie?
Yeah, I just had one question.
Yeah.
So in the original part of the question, it was converting to calories with a capital C.
Yes.
So would you accept it as kcals on a test?
Well, kcals and 1 kcal is 1 cal. They're the same thing.
Okay, so you would accept either way.
Yeah, so kcals is better actually because it tells you more about it.
Okay, thank you.
And you have to remember that the calories that we see for foods are actually 1,000 chemical calories.
Okay.
So when you see that, that beautiful quarter pounder that's 1,000 calories, it's really 1,000,000 chemical calories, which means it's enough energy to raise 1 million milliliters of water by 1 degree Celsius. And 1 million milliliters of water is the same as 1,000 liters of water by 1 degree Celsius. Or another way to think about it is it's enough energy to boil 10 liters of water. Actually more than that. 1 Whopper or Big Mac. That's a lot of energy. And that's why you need to count calories. Actually, I should be counting calories. Man, I've gained a lot of weight since COVID started. All right, Anurag, you had a question. What's your question?
All right, so for all the conversions that you're showing us, do we have to memorize all those for the quiz this week?
Yeah, you should know this one. You should know this one. You should know this one. You should know all of these. Absolutely.
All right, okay.
And so when I talk about metric conversions, you should know them all. So if I asked you, what is the relationship between a millisecond and a second, you should be able to get that. If I asked you the difference between a kilogram and a gram, you should be able to get that. If I asked you for a micrometer and a meter, you should be able to do that. If I asked you for a meter and a millimeter, you should be able to do all of those. And that's why I'm trying to teach you a way to get these rather than just teaching you to memorize them. So if you wanted this one, you would start off with 1 millisecond is 1 millisecond. And then you get rid of one of the millis. And when I say get rid of it, you actually substitute it for one of the millis, the real number. And the same for the kilogram and the gram. I start off with 1 kilogram equals 1 kilogram. Then I get rid of one of the K's. And if you memorize what K means, then you've got a conversion. So there's a way to get each of these conversions by using your noggin instead of just memorizing things. The only things you have to memorize then are M, K, D, C, M, mu, nano, and pico. And these aren't too hard to memorize.
All right, okay, that makes it clear. Thank you.
Uh-huh. Okay. So let's go to the next problem. A can of soft drink provides 130 calories. A bottle of mixed berry is 298 milliliters, has 630 kilojoules. Which provides the greater total energy? Okay, so here for the soft drink, we've got 130 calories. So I'm going to say kcals. And for the berry juice, we've got 630 kilojoules. So which is greater? And we're comparing apples and oranges. So if we convert this into kilojoules, we can then compare these two numbers and see which one is greater. Or we can convert this to kcals and we can compare these two numbers and see which one is greater. Regardless of which method we do, we should get the same answer. So let's take a look at converting kcals into kilojoules for the soft drink. Now, you may recall just a moment ago, we knew that 1 kcal is 4.184 kilojoules from the previous problem. So I'm just going to use that again. And we can estimate this answer because 4 times 100 is 400. 4 times 30 is 120. So altogether, this should be about 520-ish. Two significant figures. 130 times 4.184. And we get 540 kilojoules. I get 543.92, but because the number to the right of the 4 is a 3, I round down and make that just 54 instead of 543. Okay, so now when we compare this to the berry juice, we can say, oh, the berry juice has more calories. And that's because 630 kilojoules is greater than 540 kilojoules. So remember, the question is, which provides a greater amount of energy? If you do this calculation and you don't tell me which has a greater amount of energy, you didn't finish the problem. So there's a great answer. Now let's work from the berry juice and the 630 kilojoules, and we're going to multiply by the same conversion, but the proper way. When you're done, let me know. Okay, folks, I'm watching the news, and what I think is a decent source said that in-person learning without spreading COVID may be possible. I'll be looking forward to that. Okay, so I've gotten one response that they're done. And now we have 2. Thank you. Okay, so 630 kilojoules, I'm going to multiply by 4.184 kilojoules on the bottom so that the kilojoules cancel, and 1 kcal on top. And here we can figure that 4 goes into 600 about 150 times. So this answer should be about 150, but a little bit more because of the 30. So maybe not 150, maybe 157, 156, something like that. I don't know. So I'm going to do 630 divided by 4.184, and I get 150.57. I only get 2 significant figures, so I'm going to write 150. And here we're going to say that based on these results, berry juice has more calories because 150 kcals is greater than 130 kcals. So it doesn't matter whether we turn things into kilojoules or kcals, we get the same result. The berry juice has more. Now let's move on to this next part, which provides the greater energy per milliliter. And the soft drink has 335 milliliters, and the berry juice has 295 milliliters. So let's take a look and see which one has more energy per milliliter. So all we have to do is work with the kilojoules or the kcals, one or the other. I'm going to go ahead and work with the kcals. So for the berry juice, you have 150 kcals per 295 milliliters. 150 goes into that about 2 times. So this is going to be like 1 over 2, which is about 0.5. So let's see what we get. And I get 0.510, but I only get 2 significant figures. And for the soft drink, we're going to have 130 kcals divided by 335 milliliters. And this is about 1/3 of that. So I expect this to be closer to like 0.36 or something like that. And it's not 0.36, but it is 0.39 kcals per milliliter. So the question is, which provides the greater energy per milliliter? How do we finish this off? We would say the berry juice supplies more energy per milliliter because 0.51 kcals per milliliter is greater than 0.39 kcals per milliliter. Ran out of a little bit of room there. Any questions about that? My lights just flickered because some of the things in the house were affected by some sort of outage. It looks to me like you're still there. So if you're still there, give me a thumbs up. Okay. So if we look at these results, can you see that you get more calories per milliliter of juice than you do for soda? Could I make the scientific claim that soda is better for you because it has fewer calories per milliliter? A scientific claim. Yes or no? And the answer is no, because the evidence shows that there's more calories per milliliter for the juice than for the soda, but not that it's better for you. To make the scientific claim that the soda at 0.39 kcals per milliliter is better for you, you have to define what you mean by better. If by defining better you mean the calories per milliliter, regardless of anything else, then yeah, soda is better for you. But you have to know what your parameters are. And a lot of times people don't explain their parameters, and so they make any stupid claim that they want to. Can we claim that based on this evidence that berry juice is better for you than soda? Yes or no? And the answer is no, because this data doesn't show you that berry juice is better for you. It only shows you that there's more calories per milliliter. So the only scientific claim we can make from this is that there are more calories per milliliter for berry juice than there are for the soda. We can't make any claims to as which is better for you. If we wanted to make a claim to which is better for you, what are the things we'd have to do? We'd have to define the parameters. So we could say that one of the parameters is the amount of vitamins that each provides. Okay, and I think that would be a good parameter for health. But you have to define the parameters. And so often you see on the internet, you see on TV, people making claims where they don't define the parameters. And so their claim is valid. Yeah, soda's better for you than berry juice. That's a valid claim based on the parameter of calories per milliliter. But in my opinion, it's a misleading claim, because when people make that claim, they probably want you to think about health, but you're not. Fair enough? Good. Let's move on then. I think we'll finish off with this one. The accepted value of the melting point of pure aspirin is 135 degrees Celsius. Trying to verify that value, you obtain 134, 136, 133, and 138 for 4 separate trials. Your partner finds 138, 137, 138, and 138. Calculate the average value and percent error for your data and your partner's data. Which of you is more precise? Which is more accurate? So I'm going to write these values down. For you, you got 134, 136, 133, and 138. And for your partner, they got 138, 137, 138, and 138. When I write the degrees Celsius at the top of the table, I don't need to write the degrees Celsius for each value. Now, for the average, we're going to sum all of these numbers together. Let's see, 4 and 6 is 10, plus 11 is 21. That's 12, plus 2 more is 14. And so we get 541 total divided by 4. So the average value here is 135 degrees Celsius. Let me double check that. And I round to 2 zig figs because each of these is good to the ones. So when I total it, it's good to the ones. And when I divide by exactly 4, I get 3 zig figs. Over here, I'm not going to show you the work, but the average is equal to 138 degrees Celsius. Okay, now the first question is, who is more accurate? So that is A, calculate the average value and percent error. And who is more accurate? So the percent error for you is going to be your average value minus the accepted value over the accepted value times 100%. And I think it's fairly obvious that this is going to be 0% error. My pen is running out of ink. And the percent error for your partner, okay, new pen time, is going to be their average value, 138 degrees Celsius minus 135 degrees Celsius over 135 degrees Celsius times 100%. Wow, that is much better than the old pen that was running out. Now let's talk about significant figures for this problem. If we have 138 minus 135 and get 3, this is good to the ones. This is good to the ones. So this is good to the ones. So our top answer would be 3. Now we're going to take that 3 and divide it by 135. So here we don't look at precision. We look at how many significant figures. 3 only has one significant figure. 135 has 3, and 100 is infinite. Now you might wonder about this 135 here. Why does it only have 3 significant figures? And the answer is it's something that's measured. It's not something that is defined. So we're allowed one significant figure here, and we get 2% as our answer. So you are more accurate because your percent error is smaller. So you know how they always say bigger is better? Not with percent error, smaller is better. With ice cream cones, bigger is better. With percent error, smaller is better. Pasta is another thing where bigger is better, more pasta better. Okay, now for B, how do we do the precision? For precision, you compare average, deviation, or range. And in each case, the smaller is better. Now, hang on a second. I'm going to pause the recording here and turn that damn phone off. Okay, folks, I forgot to press the record button when I came back. And frankly, I don't know where I left off. But what I'm doing here is I'm posting what we have written before, what we wrote, so that you can actually see the information. I believe we left off somewhere around here, and we were talking about precision. So just very quickly, precision, you compare the average deviation or the range, and smaller is better. So for your partner, the range is 137 to 138, which is a 1 degree range. For you, it's 133 to 138, which is a 5 degree range. A 1 degree range is smaller, that's more precise. To calculate the average deviation, you calculate the deviation of your value from the average. So 135 is the average, 134 is this value, the difference is 1, or the deviation. Here the deviation is 1. Here the deviation is 2, 135 and 133. And here the deviation is 3. If we add these numbers up, we get 7 divided by 4 values. The average deviation is 2. And over here, the deviations are 0, 1, 0, and 0 respectively. 1 divided by 4 gives you 0. So your value is 135 degrees Celsius plus or minus 2. Your partner is 138 plus or minus 0. Smaller deviation, more precise. So your partner's more precise, but you were more accurate. So accuracy and precision are different things. All right. Thanks for listening.